So today in this video we are going to learn how to calculate R1 heat island. Okay, so in this video we are going to use Landsat 8 data. So especially Landsat 8 collection 2 level 2 data. So let's check. Okay, so let's check. So you can find different data regarding Landsat collection to tier 1 TOA reflectances and real-time data raw scene. So and this is the different kind of data set available regarding Landsat. So okay, so what we are going to use, so let's check at first RT1. So this one. So okay, just need to copy this one and paste it over there. So this is the scene. Okay, so this is the scene I'm going to use in this video. So data set availability is from 2013, and this is the collection snippet. You need to copy it from here, and this is the description. Okay, and the band is like name of the band and description and a minimum value and maximum value and unit and this kind of thing. Image properties, term of uses. So basically what is R1 heat island? Okay, so like a R1 heat island. Okay, so basically R1 heat island is when cities become significantly warmer than surrounding rural area due to human activity and urban structure trapping heat. So over there I am going to use Landsat band, Landsat 8 band. So this is the code over here. So at first input the study area, import the study area. So in this video I have imported the study area is New Delhi, which is the capital city of India. So I have imported my study area is over there. Let's check it. Just click over there and it will be so it will take few moments. So look at that, it's loading. This is the zip file I have already uploaded in Google Earth Engine and imported over there as a AOI, and then just and at first the first thing is just you need to check it over here and then copy this collection snippet from over there and just paste it. Okay, and then the similar code you need to write for your study area bound dot filter bounds and AOI. Okay, so this is the basic code for each and every Google Earth Engine code, and then you need to filter the date. So in this case I am going to use 2020. Okay, the whole year, and then you need to filter the cloud. Okay, so in this case if cloud cover is less than 20%, then I am going to use these images. Okay, so for that purpose, bounding purpose, filter bound AOI and filter date, and then filter EEE filter dot IEIT cloud. Okay, and after choosing the uh, uh, Landsat satellite image, then you have to choose the scale factor. Okay, which is available in Google Earth Engine. So you need to check it, scale factor from Landsat documentation. So which is basically over there. You need to find each and everything is from this document. I have told so many times in the earlier videos. So and then After converting all of the band using the scale factor, okay, like the band is SRV2, SRV3, this is the band name in this collection. Okay, so look at that, this is the band. Okay, SRV1, SRV2, SRV3. Okay, and then simply we need to import the thermal band, because thermal band is very much necessary for the calculating LST. Okay, so in this case you need to convert also thermal band using uh, scaling factor. So in this case STB10, let's check the band name. So band name is, look at that, this is the ST okay, B10, and then unit is Kelvin. Okay, each and everything is over there. So if you want to know more, then just view dataset catalog pages, open in another over there. Okay, so revisit interval is 16 day, and the band set is over there, B1, B2, B3, B4, B5, B6 and B7. Okay, minimum value, maximum value, and the scale factor. Okay, and offset. So this is the scale factor and offset I have used. Look at that. So this is the multiply the scale factor. The scale factor is that thing. If you convert it as a value, then it will show like a this one, and offset value is 0 0.2. So then add minus 0 point, sorry, add minus 0.2. So that the basic formula you have to use to convert each and every band. Okay, applying the scaling factor. And then let's check the band 10. So look at that, the STB10. Okay, for thermal band, unit is Kelvin, minimum value is 0, maximum value is 65535, and then scaling factor is 0.00341802. The same value I have multiply with this band over there and add 149. So this is the offset value 149. You have to add it. Okay, so I have now you I think now you got my point how I convert this band using scaling factor. So this is the basic data catalog, and each and everything you will find it over there. So as far as the scaling factor and offset value, you have to use all of this value for applying the scaling factor. Okay, and the one more thing is the pixel size is 30 meter. Okay, and after importing the band and applying scaling factor, then you have to rename as far as your need. Okay, this is the basic code, and then scaled. Okay, Landsat 8 dot map scaling. So for this code is for applying the scaling factor. Okay, and then this is the basically code is for applying the scaling factor each and every images. And then for we need to import as a median image. Okay, so for median images, so like a whatever you need to import the name as far as your need, then just you have to convert it like a scale dot median, break it on, break it off dot clip dot AOI. So okay, because I need to clip my study area using AOI. Okay, using AOI. So this is my IMG. I have uh, renamed this Landsat 8 images as IMG, and then after clip. So now we have applying scaling factor and clip our sorry, we have applied scaling factor, and then median composite we have done, and then clipping also done. So okay, so now we are going to apply from LST, from where we need to convert it Kelvin to degree Celsius. So we know In the previous video, I have shown how to change Kelvin to degree Celsius. If you want to know, then you can check the video. Okay. So for uh, to convert Kelvin to degree Celsius, so this is my image. So this one, and then dot select LST K, which is in Kelvin. So I need to convert it, my subtract it, dot subtract 273.15 and rename it as a LST degree Celsius. Okay, so till now we have done import the Landsat band as well as the thermal band and applying the scaling factor and done median composite and convert the Kelvin to degree Celsius. So let's go to the next part. So right now, for calculating the R1 heat island, we need to calculate NDVI and NDVI. Okay, so NDVI means normalized difference vegetation index. Okay, and NDVI means normalized difference built up index. So for that, so NDVI calculation, we need band 5 and band 4 in Landsat 8, as well as the for NDVI calculation, built up index calculation, we need band 6 and band 5. Okay, so this is the band 4 and band 5. So band 4 is basically red band and band 5 is basically near infrared band. So we need these two band for calculation vegetation indices, and band 5 basically near infrared and band 6 mean short wave infrared one band we need for the calculation of built up indexes. Okay, so after calculating, just a basic simple calculation, I have uploaded videos regarding how to calculate NDVI and how to calculate others kind of indices, so you can check the video in my YouTube channel. So if you have any questions, and just leave the comment in comment section. I will clarify your question. So with the basic code you have to run, like a IMG is my the base image normalized difference. This is the basic code to calculate any indices using Google Earth Engine, and you need to just import the band is SR5 and SR4. Okay, this is the band SR4 and SR5. Okay, otherwise you need to check it over there. Go to band section over there, SR4 and SR5. Otherwise you need to check it over there, Earth Engine data catalog SR4 and SR5, and then sorry, and then just rename it as a NDVI. And similarly you have to write the same code for built up index calculation. So I have said to you that to calculate the built up index you need to import the two band, one is uh, band 6 and another is band 5, and rename it as a NDVI, normalized difference built up index. Okay, and then go to classify urban versus rural using the NDVI and NDVI. So higher vegetation indices means the higher value, and lower vegetation means there is rural area. Sorry. Higher vegetation means the rural area and lower vegetation means the urban area. So we need to identify the urban area using the NDVI. Okay, so if the value is like a 0 and NDVI value is 0.02, I have calculated it as per my convenience. You can change it as far as your need. Okay, so then you need to identify a rural area. Okay, if the value NDVI value is more than 0, 0.3 or maybe 0.4, okay, maybe 0.5, if the NDVI value is more than 0.5, then it will the build up indices is very high. Okay, it means if vegetation indices is very high, then there is low built up area, and if the vegetation indices is very low, then there is a high built up area. Okay, so I classify it as per as my need. So let me tell you another time. If the vegetation indices is high, then it will be rural area, and if the vegetation indices is very low, then the built up area is very high. Okay, suppose in Delhi, I'm just giving you an example in Delhi. Okay, so this, look at this, the Bande Matra mark. This is the highly vegetated area. Okay, this is the highly vegetated area. It means there is a very low built up area. Okay, high vegetation means low built up area, and there is, look at that, there is very low vegetated area. It means highly built up area. Okay, so this is the, look at that. Okay, so this is the highly vegetated area. That is why built up area is very low, but this portion is very low vegetated area, and that is why it's a very high built up area. So you need to classify it as per as your need. So I classify it as per as my convenience, and then simply you need to, okay, calculate the mean LST. Okay, compute mean LST as per as your need. So variable R1 mean, so at first I need to calculate R1 uh, mean temperature. So LST degree Celsius is my band, that's the band. I have converted it from Kelvin to degree Celsius, and then mask from my study area is R1 area. Okay, that I have already defined it over there. Okay, and similarly you need to use a reducer for the using mean function, and geometry is my area of interest, study area, and scale is 30 meter. Okay, and then you need to go down after compute the mean LST value for urban and rural area. Okay, urban and rural area. So finally we have done identify the urban area and rural area, and compute the mean LST value for urban area, and compute the mean LST value for rural area. Okay, now I am going to print these all of the values. Okay, like print urban mean LST, print rural mean LST, and print UHI intensity urban minus rural. Okay, so these are the things you need to calculate. So, and then you need to the 9 part is the visualization the UHI. Okay, so for R1 UHI intensity calculation using the mean urban LST and mean rural LST, you have to just subtract it from urban mean LST from rural uh, mean LST. So this is the basic code. Okay, and then just UHI. Okay, so what you need to do, just LST degree Celsius subtract E member rural mean and rename it a UHI. Okay, so this is the basic code. So for printing purpose, urban mean LST, rural mean LST, and then calculation for the urban heat island pixel wise difference. So pixel wise difference to calculate, you need to uh, import and the basic formula, which is basically from LST degree Celsius band dot subtract bracket on EE dot number and bracket on rural mean. Okay, you have to calculate it from rural mean with the help of LST Celsius band, and rename it as a UHI. Okay, and then visualization purpose, like a visualization LST and visualization UHI. Okay, and use the color palette as per as you need, and minimum value and maximum value, something like that. And then center object other, and if you want to add others band like a LST degree Celsius and NDVI and NDBI and urban area and a rural area and UHI, whatever you need to apply, visualize. And then if you want to export the final UHI map, then you can export it. Okay, so the code is very basic. Each and every Google Earth Engine code, maybe I have used this code for exporting purpose. So this is the basic code to calculating the UHI. So first one is thus importing all of the band, and then apply scaling factor, and then median composite, and then convert Kelvin to Celsius and compute NDVI and NDVI, and then using NDVI and NDVI you need to identify the urban area and rural area, and then compute mean LST value, and then calculate urban heat island pixel wise using the LST degree Celsius band and using rural mean band. Okay, so this is the final main code for calculating pixel wise urban heat island map. Okay, and then visualizing purpose, and you can add each and every layer in this Google Earth Engine. Okay, and this is the final code for exporting the map. So let's run the code. So it will take few moments. So this is my study area, New Delhi, India. So I have done some mistake, maybe. Memory capacity exists. So okay, it's okay. Okay, so let's reduce these things. So I have a very less memory. So it's finally loading. So all of the layer is over there. So the first one is LST, and second one is NDVI, and third one is built-up index, and the fourth one is urban mask, and the fifth one is rural mask, and the final one is urban heat island map. So let's check one by one after loading all the layers. So you can change this value as far as you need, but okay, so to identify the urban area and rural area using built-up indexes and vegetation indexes. Okay, and then convert it, compute mean LST value for both region, rural and urban area, and then using the rural mean band. So this one, using the rural mean band, you need to calculate urban heat island, which you need to subtract from the LST Celsius band. Okay, so again I'm talking all of you. If you have any question, just leave the comment. It's all the is loaded. Just uncheck and check one by one. Okay, so this is the first band for LST in degree Celsius. Okay. So for LST in degree Celsius, I have so calculated this code. Okay, okay, this is the LST in Kelvin, and you need to subtract it from 273.15 and rename it LST degree Celsius. And then for NDVI, so for compute NDVI, look at that, I have used band 5 and band 4. Okay, so this is the value. And then build up indices. Okay, so build up indices, I have used band 6 and band 5. And then urban area and rural area. So this is the urban area masking. Okay, I have used 0.3. If you uh, as far as my need, I have used. So as far as your need, you can change the value to identify the rural area and urban area. Okay, and then rural area. So this, the rest of the places is rural area. Okay, you can change it as per as your need. And then the final code I have used this one to calculate the R1 heat island pixel wise. Okay, so you need to subtract rural mean band from LST degree Celsius band. Okay, just this one. Okay, so this is the basically airport of Delhi airport. Okay, Delhi airport which has a very high LST, sorry, R1 heat island. And then you can just giving the example which I have started from the beginning. So look at that. This is the basically Vande Mataram mark in Delhi region, which is very highly vegetated area and low built up indexes. So that is why this area is low urban heat island, and the nearest area is very high urban heat island. This area. So this area is very much, it's a railway station is over there, and the main, okay, main city actually, Hanuman Road area, as well as the other Shahid Bhagat Singh Mark. Okay, this area is nearly built up, a high built up area. So that is why this area is high urban heat island area. Look at that. These things. And if we move to Vande Mataram mark, this is very low urban heat island area. Okay, so thank you very much. If you uh, have any question, so leave the question in comment section, so I will help you. Thank you very much.